In this video, which is actually part 3 of the section 5.6, the elements of Galois theory, we are going to have a simple example to illustrate the Galois correspondence between the subfields of K containing F and tau prime, the subgroups of GKF. So actually this is the main aim of this section. The proof we are going to have only later, but we are going to consider a polynomial, because so far, I mean, in the previous video we had what is exactly K, and with the help of K that we found out GKF, K, GKF and all. But here polynomial will be given to you. You need to find what is the splitting field and then proceed. So that is the difference. There K was given, here you need to find K. So with that we will find a relation between these two. Which one will correspond to what, and then we will establish this second theorem. If K is a finite extension of F, then GKF is a finite group and order of GKF is less than or equal to degree of K over F. So for a finite extension of K, finite extension of F, that is denoted as K, this is the relation. So the relationship between the degree of finite extension and this group order. So that is what we have in this theorem. So what is that polynomial that we are going to consider? It is x power 4 plus 1 over q that we are going to consider. We will determine what is GKF, and then the subfields of K also, subgroups of GKF, everything. So here K is the splitting field of this x power 4 plus 1, not x square, x power 4 plus 1 over Q. So how to find that? Even how to find the splitting field is explained in one of the videos. So now we'll consider this equation x power 4 plus 1 equal to 0, solving which we get the roots as this. How do we solve it? We consider x power 4 on the left side, take this 1 to the other side, so minus 1, which is written as e power I pi. By De Moivre's theorem, we can have the step, but before to that, e power 2k pi I is 1, so that is introduced here. So x will be this raised to 1 by 4. Now by De Moivre's theorem, this is what you get. So when you give value for k, 0, 1, 2, 3, these are the roots that you get. So x, when you expand it out, you get 1 by root 2 plus I by root 2 minus 1 by root 2 plus I root 2. That is, this is for e power 3I pi by 4. We know that e power I theta is cos theta plus I sin theta. So here theta takes the value 3 pi by 4. So accordingly you will have cos 3 pi by 4 plus I sin 3 pi by 4. Sine is positive in the second quadrant, negative in the third quadrant. So you have, cos is negative in the second quadrant. Both are negative in the third quadrant, and here you have cos to be positive and sine to be negative. So these are for pi by 4, cos pi by 4, sine pi by 4, both take the value 1 by root 2. So you have the roots as this. So that means when you consider, see, 1 is a member of Q, no problem, minus 1 is also a member. What are not present in Q are root 2 and I. So naturally your K, which is Q of I comma root 2, will be the splitting field for this x power 4 plus 1 over Q. So now degree of K over Q can be written as degree of K over Q of I into degree of Q of I over Q. So the degree of this is 2 is known, and what is K? K is, it goes like this. You have Q, and then you have Q of I, then Q of I root 2. The degree is 2 because I satisfies this irreducible polynomial, and here the degree is again 2. So the degree is 2. Here the degree is 2. The reason is it satisfies the polynomial x square minus 2 over this q of I. So you have the degree of k, this is what is taken as k. This is what is taken as k. So degree of k over q will be 4, right? So so from this we will have order of GKQ to be 4. See actually and all this we are going to have later, that whenever k happens to be the splitting field, order of GKQ, actually the theorem what we are establishing in this video will be this only. Order of GKF is less than or equal to degree of k over f. But when can the equality be established? When k happens to be splitting field of some polynomial, or when we say that k is normal extension. All that we will come across later. So splitting field means normal extension. Normal extension means splitting field. So that we will later see as a theorem separately in a video. And here in general this is only less than or equal to, but k happens to be splitting field. So by one of the theorems which we are going to establish later, we will have this to be equal. So using that only we are having order of GKQ to be equal to degree of k over q, and that is 4. So even otherwise how we can say that? So this is one argument. Then I do not know all those things, but I want to know what is automorphism. So that we have this discussion. So we will have see, this is already determined, and then we know that sigma 1, sigma 2, sigma 3, sigma 4. So here itself when you start, you are supposed to write only sigma. Not here itself you are supposed to write let sigma 1, sigma 2, sigma 3 be the automorphisms of k. So when you can write like that, when I know this, then I can write like that. But otherwise you are going to determine only now means you will have to take that arbitrary sigma only. You cannot write directly sigma 1, sigma 2, sigma 3. So sigma, sigma, sigma only we will write. And what are the possibilities? Root 2 taken to minus root 2, I remains as such. Root 2 taken to root 2, I taken as minus I. Root 2 taken to minus root 2, I taken to minus I. And other one identity, root 2 to root 2, I to I. So these are the possibilities, and because we have 4 possibilities, we have the order to be 4, and we are taking the automorphisms as sigma 1 to sigma 4. So otherwise when you are going to determine without knowing this step, if you are going to write means just sigma only you are supposed to write. And then having got the possibilities, then you will name that there are 4 and we are naming them as. So like that you can write. But okay, so that is how it should be proceeded. But here having said this, we have this. Otherwise, as I said earlier, sigma you consider sigma, let sigma be an arbitrary element in GKQ. The possibilities for sigma, these are the possibilities. It can take root 2 to root 2, I to I. One possibility. This is one possibility. Second possibility. Third, fourth. So only you are naming them as sigma 1, sigma 2, sigma 3, sigma 4. So any general element in K should only be of this form, because I root 2. For root 2 you have this step, and for I you have this one, and I root 2 will also be there. See, you have the degree to be 4. What is the degree? Degree of K over Q to be 4. So the basis will have how many elements? 4 elements. So you have 1 root 2 I into root 2. So these are the basis elements. So according to that only we are writing this. We are not writing as such what this K is, because degree of K over Q is 4. In the previous slide we had that degree of K over Q is 4. So when you have f of AB, the elements will be of this form 1 plus or rather alpha naught plus alpha 1A plus alpha 1B, sorry, alpha 2B plus alpha 3AB. This is the theory. We are not writing this as such. This one. Using the theory only, we are writing this. So K is this, and sigma 1 is identity. So any element is taken to itself. And for this, root 2 should be taken to minus root 2. Wherever root 2, you have take it as minus root 2. So, and then I, in the next case, I, wherever you find I, replace it by minus I. And here, root 2 should be taken as minus root 2. So, root 2 is taken as minus root 2. Root 2 should be taken as minus root 2. But I is also there, so minus into minus plus, and this one I taken to minus, which you have. So your GKQ consists of all this, which is it has got 4 elements. See, when you have 4 elements, the group can be isomorphic to either AZ4 or V4, Klein's 4 group. This is Klein's 4 group. Now, why it is Klein's 4 group is all the elements will have self-inverse that can be checked, and product of 2 will be the third one that you can check. This part we can check. Sigma 2 composition, sigma 3 when you consider of arbitrary element. Sigma 3 will take that arbitrary element to this A plus B root 2 minus EI minus DI root 2. This one is written. And then sigma 2, what does it do? It takes sigma 2 takes root 2 wherever it has minus root 2. So root 2 should be taken to minus root 2. The rest should be as such. Root 2 is taken to minus root 2. So you have plus. But what is this? This is nothing but your image of the arbitrary element, that what you have considered, the image of that under sigma 4. See, these two, look at these two. They are the same. So in the same way, sigma 3 composition sigma 2, when you find, you will get that to be sigma 4. And sigma 3 composition sigma 4, when you compute, you will have, just check that. Sigma 4 takes this arbitrary element to this. Same thing only we have written here. But what is the job of sigma 4? Wherever it finds root 2, it will change it to minus root 2. Wherever it finds I, it will change it to minus I. So you have this to be root 2 changed to root 2 should be changed to minus. No, this is for sigma 3, you know. Sigma 3 means root 2 remains as such. I is only taken to minus I. Sigma 3 only we are concentrating. Here, sigma 3 only we are concentrating. It will retain root 2 as such. It changes only I to minus I. So you have minus I, and here also this. So if you look at the right side of sigma 2, it is this. So it is sigma 2. So product of, what is the definition of Klein's 4 group? It's a group with 4 elements in which product of 2 elements is the third one, and all the elements have self-inverse. So that conditions can be easily checked here. So it is nothing but your Klein's 4 group. So once you know that it's a Klein's 4 group, you can easily form the table for that identity. Then the rest, product of 2 is the third one, product of 2 is the third one, and all the elements have self-inverse. So you have this. So we can easily write down the Cayley table for that. This is what we have. Now degree of K over Q is degree of this over K here is this, which already we wrote like this. And in the same way, we can also have this. See, via Q of root 2, we can reach this. Via Q of I, we can reach this. So both we have considered. So, and Q of I root 2, when we consider that is contained in Q of root 2 comma I. So this is the lattice diagram of subfields of this that we have. You are starting from Q. Via this, you can reach this. Via this you can reach this, and via this you can reach this. So how many subfields? The proper subfields we have these three. And coming to this, you have, this is Klein's 4 group. The subgroups will be subgroup generated by sigma 2, generated by sigma 3, generated by sigma 4. So now which one will correspond to what? See, these are the subfields. We need to find subfields of K. We need to find the subgroups of GKF. Both we have got. So which one will correspond to what? That we can see. You have here. This field is this and subfields are this. Group is this and its subgroups are given by this GKF, all of its subgroups. G which is the same as GKF over here. So the subgroups we are having as, just for convenience sake, T, if you write it as T and this one as M, this one as N, then GKT, GKM, GKN that we can have. So that is what is listed here. GKT, you have T to be I root 2. T to be I root, Q of I root 2. So we shall consider G, K, T, we consider Q of I root 2. So what is the definition? All those mappings of G automorphisms which leaves the, what is the base field? Here it is this one, I root 2 as I root 2, which leaves the base field elements. Of course, you have, you can even include alpha. Alpha is a rational number. Alpha belongs to Q. And alpha times I root 2 is a member of Q of I root 2. Q of I root 2. Alpha times I root 2. All this, you can, for convenience sake, you can take it as, say, some beta. Sigma of beta should be equal to beta for all beta belonging to Q of I root 2. Like that also you can have. So which one will retain this I root 2 as such? So that we need to find out from the previous table. Not this one. Here, I root 2. See, here you have I root 2. When you consider this, here I root 2 is left as such. Here it changes. Here also it changes. Here it is the same. What is the corresponding automorphism? Sigma 4 and sigma 1. So that is what is written here. Sigma 1, sigma 4. Then coming to this, it has to fix the element of Q of root 2. So which are the automorphisms which leaves root 2 fixed? Root 2, from here also we can see this one fixes root 2 and this one. So that means sigma 1, sigma 3. Sigma 1, sigma 3. And the one which fixes I. So if you go back, you will see that this one fixes, this one fixes. So sigma 1 and sigma 2. So you have GKN to be sigma 1, sigma 2. And here all these elements will fix Q. The elements of Q as such, they won't change. You don't have any change in your ABCD. ABCD, they are the elements applied from Q. So all the automorphisms, they leave the base field element fixed as far GKQ is concerned. So your GKQ will be the entire G. Your GKQ will be entire G. So we have got the relation between these two. So this one will correspond to this, this one will correspond to this, and this one will correspond to this, and this to this. So you have singleton E corresponding to this here, only identity mapping. Whole lot if you want, it is only identity mapping. See, whole lot if you want, it is only the identity mapping, which means sigma 1. But as for the rest are concerned, this is what we have. So sigma 3 fixes root 2, sigma 2 fixes I, and sigma 4 fixes I root 2. So the corresponding fields will be this q of root 2, q of I root 2, and for V4 it is this. So this is how we give the correspondence between the subgroups and the fixed field. Rather, when we prove it, from here to there only we will be going. And in the case of cube root of 2, G, we know that this is already established in the um, roots of polynomials in that section, that your automorphism will consist of only one element, namely identity. So your GKF will also be G only. And GKF, when you consider, that will be K, it leaves all the this one elements fixed. So GKF itself is a subgroup of GKF, and K is a subfield of K. Since K is not splitting field of any polynomial, there cannot exist the correspondence between any correspondence you cannot have, because later we are going to mention that when K is splitting field of some polynomial, K becomes finite extension, and it will also be normal extension. Only then we can talk about the Galois group. So once you have Galois group only, and that correspondence that we can have. So on that we will be discussing. So the same example will be recalled later also. Okay. So when that theorem is discussed, then this will also be, this remark will be made again. So next we have this theorem. If K is it can be asked in 5 marks. If K is a finite extension of F, then GKF is a finite group. We know that already it's a group. GKF is a group, is known. So we have this to be a finite group we need to establish, for which if we establish this being finite, we will automatically have this to be a finite group. So this part we know already. Once you establish this, finite part will come, right? So our job is only to prove this part. Now let K be the finite extension given, and let degree of K over F be n. So because the degree is n, it will have bases consisting of n number of elements. So u1 to un we will take them as. Now our claim is order of GKF is less than or equal to n. This we have taken as n. So you have less than or equal to n. Suppose we assume the contrary. That is, suppose order of GKF is greater than n. That means I can have sigma 1, sigma 2 and so on, sigma n plus 1 to be the n plus 1 distinct automorphisms of K, leaving every element of F fixed. Because in GKF you have only such elements. Automorphisms which leave the base field element fixed. So now we are going to consider this set of equations needs to be remembered. x1 sigma 1 u1 plus x2 sigma 2 u1 and so on, this equal to 0. And we have from u1 u2 and so on up to un. So n plus 1 unknowns. And how many equations that we have? 1, 2, 3 up to n. So n plus 1 equations, n equations in n plus 1 unknowns. These are the unknowns. These are the unknowns. We have this. So these are n homogeneous linear equations in n plus 1 unknowns, and therefore they should have non-zero solution. That you can try with any two equations. Three unknowns here. 3 unknowns, 2 equations. You consider when you see like something like this, ax plus by plus cz equal to 0, 3 unknowns, and only 2 equations, a prime x plus b prime y plus c prime z equal to 0. So when you have 2 equations in 3 unknowns, definitely you will have non-zero solution. Definitely you will have non-zero solution, and we shall name non-zero solution means some of them can be 0 but not altogether they are 0, right? So that can be some zeros. So x1 equals a1, x2 a2, and so on. Like this we have um, homogeneous equation in n unknown. See, shall we take an example? Suppose I consider 2x plus 3y plus 4z equal to 0, and this one say x plus y plus z equal to 0. Now we will multiply this by 2 so that you will have 3y minus 2y, so y, and here plus we are subtracting, so 2z equal to 0. So y is equal to minus 2z. Y is equal to minus 2z. So you can give, say, value for z, say 1. So y will be equal to minus 2. So you have got value of z and value of y. So substituting them in one of the equations, even you can consider this x plus y plus z equal to 0. So you have x plus minus 2 plus 1 equal to 0. So your x is 1. So 1 minus 2, 1. You have 1 minus 2, 1. You are getting 0. So there exist integers. Definitely for 0 it will be 0. So you also find non-zero solution. So it has a non-zero solution. It has non. It is not, as I said first, that some can be 0. No, it is not so. All of them non-zero solutions, so that you have like this. Now from this equation we have why this one we say, because we u1 etc. un, they are basis elements. So any u can be written as a linear combination of all this. So which in turn says that we have got the solution. So I can substitute, instead of for u1 u2 separately, I can have the general one, namely u. So a1 sigma 1 u plus a2 sigma 2 u plus and so on, an plus 1 sigma n plus 1 u equals 0 for all u in k. So these AIs are non-zero scalars, which is not possible by this theorem. This is your 5.6.1. If K is a field, there exists scalars not all zero such that it is impossible, we said. That means they are linearly independent. So we get a contradiction to this theorem, and therefore our assumption that order of GKF greater than n is not correct. So it should be less than or equal to n. At the beginning we assumed order of GKF to be greater than n. So that assumption is wrong. So you have less than or equal to n, and therefore you have this. So the next video, which is going to be part 4 of 5.6, we will be having the definition of field of rational functions, symmetric rational function, and this result, this theorem, which is based on, actually the proof of this is based on the remark that we are going to make at the beginning, by defining what is field of rational functions and symmetric rational functions, and the relation between the fixed field, all that we are going to have in the next video. Thank you.